Everyone for coming. Today we had such nice talks about some deep theory of quantum information. We had some very nice applications from classical theory, some error mitigation, and today I'm going to present to you a small application that we did on how to build oracles which operate with quantum integers. And in fact, I'm going to present you some multiples of oracles. So I want to start with, right now the main branch of quantum programming is using gates. It's building quantum circuits, which is a very basic theory, very basic way of programming, which is very far from the tools that software engineers currently use in industry and research. So it's closer to other fields which have a deeper knowledge of the theory behind all of these gates, such as physicists or mathematicians, such as myself. And these researchers, these people, are not quite familiar with the attributes that good software requires to be used in an industrial level, such as quality, reusability, or composability. So the main objective of this work is to create a new set of tools which helps both of these communities. So we can help people that are currently using gates to build quantum programming, such providing software engineer support, such as providing these new tools which can be reused, can be composed, has good quality, and also provides quantum support to those software engineers who know how to use already built tools. And the point of all of this work is to be able to construct or build quantum software with improved quality attributes. So, the outline of my talk now after this presentation is I'm going to introduce a little bit of Grover algorithm, the amplitude amplification, with the implementation that it has, and then I'm going to talk about what is the multiples of oracle conceptually, and then I'm going to show you what is its implementation and the algorithm that it has, the classic algorithm to build this oracle. So, I don't know if, I hope that some of you know who Grover was. I have a nice picture of him. So, Grover is a mathematician who built a quantum algorithm which searches for a value within an unordered database with a quadratic speedup with respect to the classical algorithm. So initially, this work by Grover was just thought to be on searching for one value, but after that, a couple of years later, he published another paper which builds the amplitude amplification, which is able to search for multiple values. So this is the algorithm that we are basing our work on, such that we can construct what I'm going to talk about now. So Grover's algorithm, its implementation requires two main parts. So first of all, the oracle and the diffuser. This first part is it's just Hadamard gates to get the fully superposed state. So the diffuser is always the same, regardless of which states we are searching, whether it's one, whether it's all of them, it doesn't matter. It's always the same construction. So the main part of the circuit is the oracle, which has to be constructed ad hoc for any value or number of states that you are searching. So our point is, okay, let's search for multiples of a number. So if we treat the different states as natural numbers, such as 101 is 5 in binary, and we can keep continuing, like 9 would be written on 1001, and you can also express 3 with 4 qubits, but the more significant ones are zeros. So our oracle would mark with a pi phase all those numbers, multiples of a given number k. Okay, I'm expressing this in terms of phase oracles, However, this Grover algorithm also works just changing the amplitude of an extra qubit, ancilla qubit. But just keep with phase oracles for now. So for instance, if we had 3 qubits, a full superposition, our oracle would mark this is swapped. So our oracle would give a pi phase to 0, 3, and 6, which are the multiples of 3 in this situation with 3 qubits. So our point is, how can we generate automatically an efficient oracle which performs this operation without taking an exponential growth on the depth of the circuit. So we created this classic algorithm using 2 inputs. First one, the number of qubits, which means I want to calculate the multiples from 0 up to 2 to the power n minus 1. So for instance, in the previous one, if I have 3 qubits, I can compute the multiples from 0 up to 7, which is 2 to the power 3 minus 1. And the output is the circuit which implements this oracle. So, what is the idea inspiring the algorithm? Just think about a number, a natural number, m. We can decompose it in its binary decomposition, such as we do the decimal decomposition of numbers when we express it in our system. Just think about it in a binary system. So for instance, let's go with an example. Let's go with 23. 23 is 1, 0, 1, 1, 1. So this would be its decomposition. These are the powers of 2, and these are the values of the coefficients of such decomposition. So, is 23 a multiple of 5? We know, we can compute this very easily. We know ourselves, we can do this operation very fast. And this means that the remainder when we divide 23 by 5 is 3. So, what is the point? We know how to do this when using the decimal decomposition, but what about knowing this when we are in a binary decomposition? Okay, so let's go a bit further in this. Let's define this number, which is this Ri is the remainder of dividing 2 to the power I by k. Just keeping always in mind that this number is always smaller than k. Otherwise, we could divide once again and just up until the remainder is smaller than k. So once we define this, we can take a list for different k's. Let's focus, for instance, with k equal 5. We know that the powers of 2 are this one, up to 2 to the power 6, and the remainders go in cycles. Okay? We have 1, 2, 4, 3, and then we have 1, 2, 4 again. So for 23 in this case, we could say, okay, my decomposition is this one. So if I take the sums of all of these reminders, I know that when I divide 2 to the power 4 by 5, I get a remainder 1. So I substitute here. So if I do the same for all the reminders, what I get in the end is that these add up to 8, which is 3 modulo 5. Which means that the remainder of 23 when divided by 5 is 3. Okay? Let's think about 25. This is the binary decomposition of 25, so I can do exactly the same. I know the reminders, which are the same as previously, and the only thing different are the coefficients of 25 of the number in the binary decomposition. So in the end, I reached that 25 is equal to 5, which is equal to 0 modulo 5, which means that 25 is a multiple of 5. So, what's the point of this? All of the multiples of this number have remainder 0. So, if I want to implement this in a quantum computer, I could create something similar to this. Let me explain what all of the registers, I have 3 different registers, such that it's easier to understand. So first of all, these first n qubits, from 0 up to n minus 1, would be the qubits encoding the numbers which we want to find out whether they are multiples of the number or not. And then these qubits here, from RQ0 up to RQ nk minus 1, these qubits encode the reminders of the numbers. So I go summing here. So for instance, in 23, after all of these sums, I could have 23 up here in the register of the numbers, and 3 would be here in the register of the reminders. These two ancilla qubits, they are required to perform this modulo additions, okay? So, what would happen? After all of these sums, I know that the multiples would have a 0 reminder, as I'm performing these additions modulo k. So, the thing is that all of the multiples would have 0 here in this register. All of the qubits would be in state 0, and only the multiples, not any other number. So I know that if I perform X gates and control zeta gate, which marks with phase, I could, after this point, okay, I could have all of the multiples here marked with a pi phase and only the multiples, not any other number. And in order to be able to perform Grover algorithm and add the diffuser at the end, I have to undo these operations such that these ancilla qubits, which are used to perform the additions, are again at the 0 state in the end, so I can perform this amplification. So for instance, just keeping with 5. So I can have, having 6 qubits, so from 0 up to 5, so it would be states from 0 up to 63. I would perform these operations. So I would say, okay, I know that the remainder of 2 to the power 0 when divided by 5 is 1, it's 2, 4, 3, and then again 1, 2, and it would be the same. So I perform these operations. Now I have in these 3 qubits, the multiples would have a 0. So I mark those qubits and I undo the operations. This is in fact a very nice detail, because I add here a -1 module 5, but you don't have to really do this -1. You could perform the operation which is complementary, which means that you could just add 4, because if I add 1 and then add 4, I'm adding 5, which is exactly just keeping the same as I had at the beginning. And then after after building the oracle, we did a theoretical analysis on the depth of the circuit, but I'm going to show you the empirical analysis because I think it's better to see. So what we did is, okay, let's take qubits from 5 up to 20 and different values of k. So I want to compute the multiples of 3, 5, 12, and this number nk is the number of qubits I need to encode number k. So for instance, if I need to encode 3, I would need 2 qubits with 5, 3, and so on. So the good part that we see here is that the depth of the circuit grows linearly with the number of qubits. So with just a linear growth, I can compute numbers which grow exponentially when I go to the next number of qubits. So, for instance, from 2 to the power 19 up to 2 to the power 20 are the double the multiples that I have in the previous section. And the same goes on when we increase the number k, which is the number whose multiples we want to compute. So, for instance, you see that numbers which require the same number of qubits to be encoded. For instance, if I want to encode a number with 5 qubits, I don't know, 31, 17, all of these numbers require 5 qubits. All of them would require the same depth to compute its multiples. And we also see that this line grows logarithmically as the number k increases. So, just to make a small summary, this is our ongoing research. We've made other operations different from the multiples of, such as how to mark all numbers smaller than a different number or larger than a different number. These multiples of oracle can be composed with other oracles and can be reused again by just marking one and then marking other type of other multiples of different numbers. And what we presented is that only requires classical computations linearly on the number of qubits. So you would only be required to compute the reminders of the reminders of the powers of 2 when divided by k. You can also find the code available for constructing this oracle. It's public. It's done in Qiskit, so if you want, you can just try it. And as a future work, we would like to keep going on creating this type of oracles or other type of software that can be used by other people as well, providing the good documentation. And also we are on the step of creating these bigger operations. And we would also like to keep exploring operations with integers. It's like more or less the main objective that we have, and to keep continue in this line. So, thank you for your attention. I hope that you like it.
Thank you.
So thank you very much, Javier. It was a wonderful talk. The talks are actually planned without discussion, but if there's any pressing question, of course you can ask now. We have some time maybe for one question. Otherwise, the idea was that everyone who presented a paper will present his paper also at the poster session, so they're bringing a poster with them, and later on you can go to the poster session, speak to the authors, and have a more detailed and more deep discussion than just for one question. But if there is a pressing, we can now ask Javier.